Alright, so in this video, we're going to address bases and basis vectors. Now, let's take a moment and recall what does it mean to be a basis. It means that the set is the set of vectors in order to be a basis can act as a good coordinate system for that space. So let's say we're in three-dimensional space or R3. I have these three vectors here. This right now acts as a basis for R3. And what that means is that two things are possible. One is that I can actually get to every point in R3 by somehow combining these three directions. I can go here, up a bit or down, forward or back, this way or that, and I can get to everywhere in R3. Um, it also means that, so in order for this to work, I need to have enough vectors, right? They have to span R3. If I take one of these vectors away, then I can't go up or down. If I can't go up or down, I can't get all of R3. That's not a good coordinate system. On the other hand, if I add in an extra vector, then that's kind of weird because now, like to get to this point, if you can see that, in order to get to this point, I could go along this vector, or I could take a different route there using this vector and that vector. And that means my coordinates don't uniquely point out points, that each point in my space can have different coordinates, and that's bad too. So the two properties that define what it means to be a basis or a good coordinate system is that it spans and that they're linearly independent, right? I can't take some of these coordinate vectors and make the other one with them. So if I'm looking at my set of vectors here and I ask, is that a basis for R4? What I'm basically saying is that if we want to rewrite in terms of vector properties, let's give this set a name S. What I'm basically saying is S is both linearly independent and spans R4. Alright, and so if I want to see if it in fact does this, what I need to do is take my augmented matrix, or not take my augmented matrix, make a matrix of take my matrix of values and find its reduced row echelon form. So if I do that, then I'm looking at is a 4x4 matrix whose entries are 4, -3, 1, 2, -5, 1, 4, -4, -3, 4, -4, -6, -2, -3, 2, -3, and my reduced row echelon matrix is 1s across the diagonal, 0 elsewhere. Now, let's see what this is telling us. So remember, uh, we want these four vectors here that in these four columns to both be linearly independent and span. And so we have to go back to our previous sections and ask ourselves, if I take the reduced row echelon form of this matrix, do I satisfy both the linear independence and the spanning? So, as far as linear independence goes, if I were to pretend that I was trying to solve a vector equation where the first three columns were being combined to make the fourth column, what this bottom row tells me with the zeros and the 1 is that there are no solutions to that, right? So what I can say is that we observe that the vectors are linearly independent sorry, at this point we're working on B. And so it satisfies one of our criteria. Now the other criteria is to see if it spans. And if you recall, what we're looking for in spans is that I don't want to see any zero rows, right? If there's zero rows, then there could be vectors where right? If I had a zero row, then there could be a way to pick a vector so that the linear combination of these four vectors couldn't achieve the fifth vector. But what we look at here, we don't have a zero row, we have this as a row. So we also see that the vectors span R4, thus these vectors form a basis. Alright, thank you very much. I'll see you in the next video.